Welcome. This is a recorded session of the Post-Quantum Cryptography Conference of the PKI Consortium, which took place in Kuala Lumpur, Malaysia. This conference is made possible through the support of the PKI Consortium Post-Quantum Cryptography Working Group and our sponsors SSL.com, Entrust, Keyfactor, HID, and Crypto4A. And with exceptional organizational support from SSL.com, Keyfactor, Logius, POS Digicert, Baker Tilly, MSC Trustgate, and Digitaurus. Join the discussion. Join the PKI Consortium. Go to pkic.org/join.
Our next speakers, we have two individuals that I've actually had the pleasure of knowing from the National University of Singapore for a little while. Their talk is entitled Quantum Safe Network Testbed with Versatile Reference Applications. Here we have two senior research fellows from the National University of Singapore. Starting off will be Dr. Jingyan Ha. He's a senior researcher and technical lead at the National Quantum Safe Network Center for Quantum Technologies in Singapore. He has over a decade of experience in quantum science, focusing on KQD, security validation, and quantum safe standards, amongst many other things. Numerous publications to his credit. Again, I've had the pleasure of knowing him, and I think you'll find him very interesting. Also joining him will be another senior research fellow from NUS, Dr. Hao Kin, who is affiliated with the Center for Quantum Technologies within NUS. Also equally skilled in a variety of areas of quantum computing, KQD, and is currently the co-chair of Quantum Communication Network Task Force under Singapore's IMDA agency. So without further ado, I'll introduce Dr. Jingyan Ha. Thank you.
Yeah, thanks for the very nice introduction. So again, a warm welcome to everyone to this presentation, and it's my great pleasure to be able to share with you our latest work in the National Quantum Safe Network, where we showcase how we do trials on the quantum safe technologies, including quantum key distribution, QKD, and as well as post-quantum cryptography, PQC. So today I'll be first sharing about how some of the background and how we built the testbed. And then afterward, my colleague, Dr. Hao Qing, he will share with you more about the standards underlying and also the reference use cases that we use, that we deploy on top of this testbed. Let me get my clicker. Yep, okay. All right, let's get started. So perhaps let me just kickstart by defining the term quantum safe. So when we say quantum safe communications, we are really referring to the fact that in the era where we have large-scale quantum computer, or sometimes being called CRQC, cryptographically relevant quantum computers, being ready, how can one still communicate securely or safely? So quantum safe means that the means of communication where such a situation, the communication remain intact or secure between the two parties. So here we have two approaches. First is with software, another is with hardware. For the software, it will be the post-quantum crypto, PQC, where the algorithms basically they are designed to be resistant against quantum computers. Yeah. Meanwhile, for the hardware approach, QKD, quantum key distribution, we took another approach whereby the security is guaranteed by the law of quantum mechanics. And as long as the implementation is being done faithfully to the protocol, in theory, the security will be even remain secure against an unbounded adversary in terms of computational power. Last but not least, there's a random number generation, which here we will advocate to use a true random number generators, if not using a quantum random number generators, whereby intrinsic randomness can be obtained to act as a seed for both, or the keys for both the QKD and the PQC solutions over here. So for Singapore, it has quite a long history, more than 10 years, about close to 15 years of efforts in quantum safe communication. So it starts off as early as a demonstration of free space QKD across the, let's say, I think here, campus with entangled photon pairs. And then later on, there are efforts on fiber infrastructure with quantum key distribution, satellite-based QKD, and so on. So in the process, the Center for Quantum Technologies, a center of excellence for to explore basic science and also the applications of quantum tech was formed in 2007. And then there are a few other different quantum communication-related companies are being established as well, such as Spectra, S15 Instruments, Square 8, and so on and so forth. And for us, NQSN, so building on all these results, so we launched at 2022, and it's a nationwide project whereby we aim to build a testbed for trials of quantum-safe technologies. And since then, there's also a few other efforts, such as NQSN Plus, which we will explain a bit more, which is a business edition of our testbed. And then now our project has entered phase 2, which we will elaborate further right now. So just to get all of us on the same page, so here we would like to quickly introduce what is a quantum key distribution. So assuming here we have two parties, typically the Alice and Bob would like to communicate with each other securely, assuming there's a CRQC presence. So what happens is that they can actually deploy, utilize QKD technology to ensure that their channels to ensure that a pair of symmetric key can be created or established on both parties in a secure manner, secured by the quantum key, quantum physics. And here, upon the protocol, completion of the protocol, they will have a pair of identical keys. And with that, they can use it for applications such as symmetric key encryption based on one-time pad or advanced AES, advanced encryption standards, and so on. And this will form a quantum key encrypted communications. And the security lies on the fact that if there's an eavesdropper trying to tamper with the channel in between during the communication protocol, for example, here, let's say, trying to tamper with the quantum channel or try to exploit or copy the quantum signal that is being transmitted, what happens is that because thanks to the law of quantum physics, such as we say the no-cloning theorem or the uncertainty principles, so the eavesdropper inevitably will leave a fingerprint on top and increase in the what we call a quantum bit error rate of the system. And if it exceeds a certain threshold, the Alice and Bob, they will be able to see the statistics therein, and then they will deem that the transmission of the key or the generation of the key is not secure, and they will abort the protocol. And hence, this is where the security lies. And so this is what we can say, meaning that is QKD provide a tamper-evident method to establish a pair of symmetric key, and it also can be proven to be information theoretic secure, meaning that regardless of the Eve's computational power, be it with the quantum computers or whatever computer, unbounded, it remains secure based on the protocol. So let's see what will happen if we put QKD and PQC side by side for the sake of just comparing their features. So here we see that the both sides, they do share some great similarities. For example, the PQC side, especially the CAM, is for key establishment, QKD as well. And then we also see that in terms of the standardizations, both definitely require, as we have also heard throughout this conference, a good standard that to allows for interoperability. And of course, QKD will necessarily require hardware, but in terms the pro part is that it will get to enjoy the so-called information theoretic security, ITS, as compared to the PQC, which is computational complexity-based security. And both will, of course, need to address their implementation loopholes as the technology being rolled out. For the National Quantum Safe Network, this is our main objective and motivation. So as alluded a while ago, so we are aiming to build a nationwide terrestrial network. And then this phase, we are trying to extend to optical ground station, to satellite communications for trials of the technologies. And here we have more than 30 companies and government agencies being involved in our project. And our goal is to try to achieve an interoperable quantum safe network. And hence, we target vendor neutral, multi-protocol, and also look at the QKD and PQC and the hybridization therein. And we also build readiness by developing the national and international standards or best practices. And in between, we also evaluate the function and the security of the devices. So this is how our geographical map looks like. So you can see we have covered with the central node at the south side of the island, so which is where the NUS Center for Quantum Tech lies at. So the rest of the locations are basically covering the northeast and west. And here, let's zoom in. So if we look at the topology itself, you can see it's so we have around 12 nodes and still expanding, a star mesh type of network over here. So you can see there's a small mesh that is being established, where a mesh topology will allow for resilience if there's any in-between link that is not available. And we have right now more than 75 dark fibers that will allow for the trials and the deployment of the technology, with total fiber lengths more than 1,500 kilometers. And to evaluate these technologies in various conditions, so we also have a distance of variance range from less than half a kilometer to more than 45 kilometers. In terms of the testbed, let's zoom in to our architecture. So we are following the basically the ITU-T Y3800 series and also the our reference specs by the local agencies. So here is in a layer structure where we have on first the quantum layer creating and establishing the quantum technologies underlying, and this is built on top of existing fiber infrastructure. So meaning that there's no new fiber being laid, and we can just use the existing fiber for this technology. And then on top, we have the network and the key management layer that will serve as the routing of the keys, which we aim to be interoperable and also scalable. For the applications, so we work with a lot of the different technological vendors to consume and also to utilize the key and to show that how all these existing classical encryptors can also be made quantum safe just by seamless integration with the existing network over here. And on top, we also have some testing by, for instance, here VRV and Keysight. So here's a virtual lab tour, similar to the speaker before, so we couldn't bring everything to showcase. So here's a photo. So you can see we have the quantum devices being deployed, quite a few of them. Later on, I'll zoom in. And also the network appliances, the encryptors, and also some of the testing devices. And if we look at it layer by layer, first looking at the quantum layer. So on the quantum layer, we have the opportunity to evaluate and also to install, procure different types of quantum key distribution system. So here, for example, we have system from ID Quantic, Toshiba, Quintessence Lab, and also S15 Instruments, and our own in-house developed QKD system that utilizes entangled photons. And apart from evaluating their functionalities on the testbed, we also test their performance, let's say over here, over a wide range of loss values. And we showcase that, let's say over here, a typical performance of hundreds of kilobits per second can be achieved. In terms of the key management layer, this is one of the most critical components in our network, because as we aim to be vendor neutral and multi-protocol, key management system that is able to support such a requirement is necessary. So here we have developed and also in-house and also evaluate third-party key management systems. And for our key management, so it has multi-input, multi-output, and the KMS, the links are also being secured by the TLS 1.3 X25519 hybrid MLChem 768. And for the certificate, we are still using the existing S.509 certs. For the key management system, there are the key management agent and also the key supply agent. Each basically facilitate the transport of the key, could be based on OTP or highly secure transmission methods, and also we are ensuring that the key supply is in compliance with the ETSI 014 standards. So for the equally important, the control and network management. So basically, we also need to ensure that these devices themselves, they also have a very robust routing protocol mechanism that is also based on our policy that is being set. And you can see that here we also have the telemetry that is monitoring the link, basically the QKD network health status, the link, the key storage, the key rate, and also even the device temperature. An ad hoc applications that we'll quickly introduce as well. So here we have also a randomness beacon, which is based on quantum random number generators by S15 instruments. So here, this randomness beacon basically allows us to have a public verifiable source of randomness. Of course, not for cryptographic purposes, but it can be used for, let's say, electronic voting and audit purposes and so on. So we welcome you to try out as well. And now I'll pass the time to my colleague, Dr. Hao Qing, to introduce to you the next steps.
Hello. Thanks, Jingyan, for the previous foundation introduction. So I take over here. So I will start to introduce the standard activity. So instead of the QKD standard, I will first start with the PKI standard, which is kind of related. I'll explain you why it's related. Right now, I'm not sure everyone aware. So there's a 3 standard related to the PKI certificate on the under development actually in ITUT and ISO. So in general, these 3 documents are all related, and now is planning for the PQC migration in the near future. And the reason I mention this is because mainly that now in ITUT, as you know, the X.509 is mainly from born from ITU back to 1988, and still ITU still developing and maintenance this document. It has many revision and corrigendal amend, but so far this has still been under maintenance on the ITU and ISO. So for the QKD related standards, it's actually happening now in the same working party, very interestingly. So in this working party 1, we have the PKI standard digital entity and as well as a quantum-based security. So every year, so since 2001, so ITU now celebrates the X.509 day, which happens either on 9 May or the September 5th. So in this year's edition, so actually the PQC migration on the standard level is one of the main topics to discuss there. So otherwise, we actually have some progress in the X.500 series that, including the X.508, is already in the document has been mentioned the quantum computer threats and also the possible attacks and how to do the migration, some idea on do the migration. And the X.510, it has been, the wrapper protocol has been included for pass for the crypto algorithm to be smoothly to integrate with a stronger cryptography algorithm, which is PQC is some example. So in the annex, there's also some migration strategy and the quantum computer threat analyze. Then back to the everybody's concern about the X.509. What is the when the PQC will be included? And I think it's under development, as I mentioned, but I think it's going to be soon. So I think even maybe in the next month's ITU meeting, likely there will be some update on the amend 2 of the X.509. The PQC algorithm could potentially to be there. Apart from this, I will move to the actual QKD standard activity that we are involved. So actually, as I mentioned, that in the ITU SG17 working party 1, there's a PKI and QKD standard activity. So one of the activity we are leading there is on the QKD protocol framework standardization, which will be the first QKD protocol related standard. So unfortunately, QKD has been invented for more than 30 years, but there's no protocol level standard. So that's with, this standard will be likely the first one. Other than that, we also have been involved in the other key concepts, such as the security requirement of the trusted node in the implementation. Also in the ISO IEC, there's one document already published on the security requirement and evaluation. So this is our international engagement on the standardization activity. And we also conduct the local standard efforts that in partnership with the local government agency, IMDA, that we have adopted the international standard practice and formalize the local standardization guideline for the QKD network implementation. So this figure is one of the fundamental architecture for QKD network that also align with what Dr. Jin Yans mentioned on our network architecture with quantum layer, key management layer, network management control layer, and application layer. That this is already has a great consensus among the international community and has been adopted in kind of standard sense. So far this is a standard introduction. That is, many people ask if QKD is a new technology, if any standard guidelines. The answer is yes, and also this progress is undergoing. In near future, there will be likely more standard to support the adoption and the usage of this technology. Other than that, I will move towards some use case that has been demonstrated over the NQSN testbed in terms of key management starways. So we have demonstrate different kinds of key management use case and solution over our testbed, including our own KMS to enable interoperability of different kind of QKD technology and to enable the scalability key relay among the QKD network. We have also worked with the Evolution Q to demonstrate their own KMS solution for QKD purpose. On top of that, we also demonstrate with a Canadian company called Quantum Bridge that demonstrates distribute symmetry key exchange protocol that based on secret sharing for the cross-border key distribution between Toronto and Singapore. Besides that, there's very recent progress that we have working with a company Viavi to develop their testing suite on how to evaluate the robustness of the key management system in the QKD network and how this we basically adding the traffic through the VPN tunnel and evaluate how the KMS is capable to support the key for the encryption tunnel. So this is activity on the KMS related use case. Then we move to the application layer that we have several demonstrations. The first one is that in Singapore we have demonstrated the feasibility that for the QKD technology to be deployed over the data center environment. This is one of the, I believe, the first few tests in the data center environment in Singapore that we demonstrate that the key can be established, and also we have some cloud-based application to showcase this is based on the infrastructure and environment of a